Now that we've taken an initial look at what happens to mass on a spring over time, we're going to adjust our model a little bit and look at the question, how do we model damped motion? And let's look at what we mean and how that impacts our differential equation. What we did before is we had a spring attached to a mass that was just allowed to bounce freely. There was an equilibrium point, and we had this initial stretch distance we called x, and there was an initial velocity reached of v sub 0. What we're going to do to change our model, though, is we're going to attach this mass to something called a dashpot. And the dashpot is something to absorb the shock or the bounce of this system, encouraging it to get back to equilibrium. And we say that the dashpot can absorb some dashpot constant we'll call beta. And it turns out that the damping constant that dampens the bounce and the motion is proportional to the velocity. In other words, the force, or the damping force, we'll call it F sub d, is equal to negative beta times the velocity. But we know velocity is equal to the first derivative of the position, which means if we put this together, the entire force in this system is going to be the force of the spring plus the force of the damping motion. Well, we know the entire force is mass times the second derivative. We know the force of the spring from Hooke's law is a negative constant times x, and we said that the damping force was equal to negative beta x prime. Making this equation equal to 0, we would have the mass times x double prime plus beta times x prime plus the constant times x equals 0, which has auxiliary equation of m, let's use r for the derivatives, mr squared plus beta times r plus the constant equals 0. So now we've got a familiar looking equation. And this equation really has three cases for possible solutions. There could be two real solutions. If there's two real solutions, we already know that the equation is going to be of the form x equals c1 e to the first root times t plus c2 e to the second root times t. And in this case, the graph is going to look like this, where it's going to basically dampen down immediately to equilibrium. Or maybe there'll be an initial velocity that shoots it below equilibrium, but then it's going to go right back to equilibrium. There is going to be no oscillation on this graph. And we call this overdamped. There is enough damping force to pull this spring, or this mass on the spring, directly to equilibrium. The other option that could come out, and it's not too often, but it does happen on occasion, where we get one repeated real solution. Maybe our characteristic auxiliary equation is a perfect square. We know in that case the solution then becomes c1 e to the root times t plus c2 times t times e to the rt And the reason for that is to make both of them linearly independent with the two possible solutions. In this case, we have a possibility that we could pass equilibrium at most once. So it might start going up, pass equilibrium, and go right back to it. Or it might even just go straight to equilibrium. But it turns out that it passes equilibrium at most, though not necessarily at all, once. We call this situation critically damped. And the reason we say it's critically damped is if there's any slight variation on the damping constant, we end up with what is called overdamped, where we have two complex solutions. And we know with the two complex solutions, that's of the form x equals e to the at, where a is the real part, c1 cosine of bt, which is the complex part, plus c2 sine of bt. And if this is the case, the graph, the damping, the dashpot does not have enough absorption to absorb the entire vibration all at once. And so what happens is the graph is going to start to bounce around as it gets closer and closer to equilibrium. We're going to say that it oscillates, but not forever, towards equilibrium. And we call this case the overdamped case. This is what you'll feel when you hit a pothole and the car bounces up and down a little bit. You feel that bouncing motion. That is the two complex solutions of the overdamped dashpot. All right, your book does show an example of each of these three cases. We're just going to do one because we already know how to solve all three of these cases. We just need to make sure we know how to set them up. So for our example, we're going to say a 16-pound mass is attached to a 5-foot spring, stretching it to 8.2 feet. It is released, in other words, time is 0 at that point, 2 feet above equilibrium, and the resistance from the dashpot is equal to the velocity. So let's take a look at solving it. First thing we need to do is find the spring constant, and we get that from Hooke's law. Hooke's law tells us that the force is equal to a negative constant times the stretch. The force was the 16-pound mass, and it stretched it from 5 to 8.2. And be careful, x is not 5, x is not 8.2, x is the stretch. It stretched 3.2 negative so that the constant becomes positive. So when we divide 16 by 3.2, the constant is going to be equal to 5. We also need to know the mass from that 16-pound weight. Remember, we take the weight of 16 and we divide by gravity's constant, which is 32. So the mass is 1/2 of a slug. Then we can think about our differential equation, that the mass times the second derivative plus b times the first derivative plus our constant times x is equal to 0. Plugging in what we know then, the mass is 1/2 of a slug times x prime prime, plus beta is, if the resistance is equal to the velocity, beta is going to be equal to 1 x prime. So we have 1 resistance, 1 velocity, plus our constant, which we just found out was 5, times x. Now, I don't like having that fraction out front, so I'm going to go ahead and multiply everything by 2. So I'm solving a system with no fractions. All right, the characteristic equation here is r squared plus 2r plus 10 equals 0. That's not going to factor, so you could use the quadratic formula, but I'm going to complete the square just because that's going to be quicker. Move the 10 over, and to make it a perfect square, we take half of 2 and square it. Half of 2 is 1. 1 squared is 1. So I'm going to add 1 to both sides. So I have r plus 1 squared equals -9. Take the square root. R plus 1 equals plus or minus 3i. So r is equal to -1 plus or minus 3i. We know then that our solution is written in the form x equals e to the a, which is the real part, -1t, times c1 cosine of b, which is 3t, plus c2 sine of 3t. And now all we have to do is solve for our constants. To do that, we know it's released initially 2 feet above equilibrium. So we have this initial point of 0, -2 because it's above the equilibrium. Remember, we defined a positive as down with a stretch, -2 because it's above. And we also have information about the velocity. Let's find c1 first. Let's plug this in. -2 equals e to the 0 is 1. c1 times 1 plus c2 times 0. So we just have -2 is c1. It is just released. Interesting. There's no initial velocity. So the initial velocity is going to be equal to 0. We're just letting go. It's just released. So we're going to find x prime. And then we're going to plug in the point 0, 0. Because at time 0, there was no velocity on it. We're going to have to use the product rule here. So we have -e to the -t times c1 cosine of 3t plus c2 sine of 3t plus, going on to 2 lines here, running out of space, e to the -t times the derivative of the second part, which is -3 c1 sine of 3t plus 3 c2 cosine of 3t. And when we plug 0, 0 in, we get -e to the 0, which is -1 c1, because the cosine goes to 1 and the sine goes to 0, plus e to the 0 is 1. The sine goes to 0, but the 3c2 cosine going to 1 leaves behind a 3c2. Well, we already know that c1 is -2. So we can subtract 2 and divide by 3. c2 is -2/3. So we're going to end up with our final equation for this dashpot system, this damped motion, is e to the -2 times c1, which is -2 cosine of 3t, plus C2, which is negative 2/3 sine of 3t. We also know because we had these two complex solutions, the system is overdamped, which means we would expect the graph of this to oscillate and bounce all over the place. So let's take a look at talking about really quickly what this graph is going to do over time. As this graph oscillates around equilibrium, it's going to start off with a big amplitude, and then over time, the damping force is going to get it back to equilibrium. So we don't really have a period and a frequency and an amplitude, but we kind of sort of do. And so we're going to call this the quasi period. And the quasi period is still going to be 2 pi divided by that omega value. So in our case, 2 pi divided by 3. So every 2 pi over 3 seconds, approximately 2 seconds, this spring is going to bounce up and down. It's just not going to bounce as far. We can also talk about what we might refer to as the quasi frequency, which again is just going to be the reciprocal omega divided by 2 pi. In this case, 3 divided by 2 pi cycles per second. So about half of a cycle in a second. And then we can also talk about what's going to be the damped amplitude. And it's the equation that models how tall this graph is going to be. And the way we're going to define the damped amplitude is we're going to call it A times e to the AT that we just found up above, where the A, similar to before, is the square root of the constant squared, c1 squared plus c2 squared. So in our case, we can calculate the A is equal to the square root of negative 2 squared plus negative 2/3 squared, which is going to be 4 plus 4/9. So to get a common denominator, I'll multiply by 9 over 9. 9 times 4 is 36, plus 4 more is 40 over 9. And so we get the square root of 40 over 3. And if we wanted to, we could simplify that radical. That's 2 root 10 over 3. So our damped amplitude, then, would be the equation x equals 2 root 10 over 3 times the e to the a, which is negative t. And it's going to be plus or minus that. And how that works out on the graph is it's almost like the squeeze theorem from calculus. This graph is going to be squeezed in between two curves. One of them is 2 root 10 over 3 e to the negative t, and the other one is negative 2 root 10 over 3 e to the negative t. Let's take a look at the graph and see what it looks like. All right, if we graph this on our Desmos calculator, we see what happens is the graph starts 2 feet above equilibrium, and remember we defined above equilibrium as a negative x. Then it's released, and since there's no initial velocity, the spring is going to initially pull it back towards equilibrium. But because this is an overdamped system, it's going to overdamp too far, and it's going to start to bring it back towards equilibrium. But again, because it's overdamped, it'll go too far, but not quite as bad before as it starts to oscillate back towards equilibrium. If we turn on that damped amplitude equation that we just found, you'll notice at the top and bottom, what this does is show you where the amplitude is going to be squeezed down back towards equilibrium. All right, it's your turn to practice some of these before we get to adding a driving force that's acting on the system over time. But first, we want to get really good at damped, underdamped, overdamped, and critically damped motion. Take a look at the assignment, and good luck.